Hello, friends. Welcome back to my next session on packing in solids. So, today we shall see how the three-dimensional arrangement of particles in a solid is done. So, our topic for today is three-dimensional close packing. I hope you've already seen my earlier session on the two-dimensional and one-dimensional packing. So, with that background, let us go on into the three-dimensional close packing. Now, if you haven't, you will fail to understand what I'm teaching you today. So please find the link of the previous session and have a look at that earlier video before you proceed with today's session. So we'll take up the first type of three-dimensional packing that is called as the AAA type of packing. Now, what is the AAA type of packing? This comes from the two-dimensional close packing of the AAA type. So if you remember, in the two-dimensional AA type of packing, we saw that all the rows are identical to each other. That is, the first row, the second row, the third row are aligned in such a manner that the particles come exactly one above the other, thereby making all the rows identical, and hence this two-dimensional packing is called as the AA type of packing. Now, when we convert this into the three-dimensional type of packing, then what happens? Two or more such layers are placed one over the other. So when the layers of two-dimensional packing are placed one above the other, we get what is known as a three-dimensional packing. Again, wherein the first layer, the second layer, the third layer are all exactly identical to each other, and the atoms are arranged in such a manner that they lie exactly one above the other. That means they are in the same line. So when you have this kind of an arrangement, this is known as the three-dimensional AAA type of packing, and the coordination number in this type of packing is 6. Now coming to the two-dimensional close packing of the ABAB type. Now in this case, we have already seen that the row A and the row B are not identical. Reason because the second row fits into the depressions of the first. Now, because the second row fits into the depressions of the first row is different from the second, and it is similar to the third row. So I can name this as the ABAB type of packing, which you've already seen. Now, if I were to convert this two-dimensional packing into the three-dimensional packing, then what would happen? But in order to understand that, we should know that whenever we arrange the packing or the atoms in the two-dimensional way, it gives rise to two types of voids. Okay, now what do you mean by voids? Voids are nothing but empty spaces. So when the rows fit into the depressions of the other, and then let us say I'm placing the second layer above the first layer, okay, a layer of the ABAB type represented by the dark blue rings, and we have a layer of the ABAB type represented by the sky blue colored rings. Now, if these two layers are placed one on top of the other, you can see that it gives rise to empty spaces between the particles. Now these empty spaces are of two types, which is denoted here by O and T. O represents the octahedral voids and T stands for the tetrahedral voids. Now what do you mean by this octahedral and tetrahedral voids? Now if you were to observe this particular void carefully, okay, you will notice that this void is formed by total 6 spheres. There are 3 dark blue colored spheres in the bottom layer and 3 sky blue colored spheres in the top layer, such that these 3 triangles, I mean the 3 spheres form triangles with the apex pointing in opposite directions. Okay, so in this case the apex is pointing in this direction, whereas in the sky blue case the apex is pointing in the downward direction. So when you have atoms arranged in such a manner, then the empty space that arises between these atoms is termed as an octahedral void, which is formed by 6 spheres. Whereas a tetrahedral void is one where only 4 atoms are involved. So as you can see, this particular tetrahedral void, there are 3 spheres of the dark blue color, that means in the first layer, and there is only 1 sphere of the sky blue color on top of it. So when this 1 sphere of the second layer is placed over the first layer in such a manner that a void or an empty space is generated by the arrangement of these 4 atoms, 3 in the bottom layer and 1 on the top layer, or vice versa, then this kind of void is called as a tetrahedral void. So a tetrahedral void is comes into existence due to the arrangement of 4 atoms, while octahedral voids come into the arrangement due to formation of 6 atoms. Now, the name tetrahedral and octahedral has been given because when you take the centers of the atoms that are arranged, okay, and you join the centers, then in this case you will see a tetrahedral geometry, and that is why it is called as a tetrahedral void. And when an octahedral void is formed, if you take the centers of the spheres which are responsible for forming this octahedral void and join them together, it will give rise to an octahedral geometry, okay, having 8 faces, and that is why this void generated is also called as octahedral voids. But in reality, octahedral void is formed by 6 spheres or 6 atoms, whereas a tetrahedral void is formed by 4 atoms. Okay. All right. Now moving ahead. Now suppose a third layer is placed on this second layer. So already you can see here these white colored spheres, they form the first layer, which is of the ABAB type, because the first row and the second row are not identical. The second row is fitting into the depressions of the first row. So this is a ABAB type of two-dimensional arrangement. Then on top of it, I have the black layer of atoms, which denotes the second layer of the ABAB type, upon which I'm placing once again the third layer on the second layer. Now, in this case, when this third layer is placed in the second layer, the placement of the third layer can be such that it may cover either the tetrahedral voids or it may cover the octahedral voids that have been generated. So in the previous slide, we understood how these octahedral and tetrahedral voids are generated by placing the ABAB layers one on top of each other. So if the third layer covers the tetrahedral voids that have been generated, then you will see that the third layer is identical to the first layer, and then it gives rise to what is known as the hexagonal close packing, okay, or it is called in short as HCP. So I have denoted this hexagon here, okay. So this will give rise to the hexagonal close packing of the three-dimensional type when the third layer covers the tetrahedral voids formed in the placement of the second layer over the first. Whereas if the third layer were to be placed in such a manner that the third layer covers the octahedral voids that are generated by the placement of second layer on the first. Okay, so here this figure C, I've denoted it as capital C. Now this C, I've named it as C because when I play the C represents the third layer, and when I place the third layer in such a manner that it is covering the octahedral void. So you can see here these 3 black spheres, okay, and below it you have 3 white spheres. So the total 6 spheres are giving rise to the octahedral void, and this C is covering the octahedral void. So when I place the third layer in such a manner that it is fitting on the octahedral voids or it is covering the octahedral voids, then the alignment of the third layer is different from that of the first layer. It does not match the first layer. So I can call this as A layer, B layer, and the third layer will be represented as a C layer. Okay, so in the earlier case over here, you saw that A, I've represented it as A here because this is covering the octahedral void, sorry, the tetrahedral void. Okay, so here it is not present in that same position. Rather, it has shifted to another position such that it will now cover the octahedral void. And hence the alignment is different from that of the first layer. So I can call the third layer as the C layer. So this is a new type of three-dimensional arrangement, which is called as the cubic close packing. Okay, it has given rise to a cube. I have shown you how the cube, the unit cell is a cube here. Okay, so this cubic close packing, three-dimensional packing we are getting, which is of a different type, that is also denoted as ABC type of three-dimensional packing. Whereas the hexagonal close packing HCP will be represented as AB type of three-dimensional packing. Okay, so these are the two types of three-dimensional packing. In both the cases, the coordination number is 12. So if we just have a closer look at, or a detailed look at the hexagonal close packing, that is HCP. So here you can see the green layer represents the A layer or the first layer of two-dimensional arrangement. Then we have the second layer of two-dimensional arrangement represented by the blue. Okay, and once again I have this border outlined, darkened border layer that again represents the third layer. And as you can see, the third layer is covering the tetrahedral voids here. Okay, so when the tetrahedral voids are being covered, the placement of the third layer is such that it covers the tetrahedral voids and not the octahedral voids. Then the third layer is identical to the first, and this gives rise to the AB type of three-dimensional packing, which is also called as hexagonal close packing. Now, as you can see here, this central atom, okay, in the middle layer is, or in any layer for that matter, will be in contact with 6 other atoms in the same layer. And plus, there will be 3 from the top and 3 from the bottom, which it will be in contact with. So that means in all, this central sphere is in contact with 12 other atoms, and hence the coordination number in HCP is 12. Now, if you also observe the apex of these 3 atoms from the A layer and from the A layer at the bottom, okay, they are pointing in the same direction. So this gives rise to a HCP kind of a packing, which covers up the tetrahedral voids formed in the second layer. Now, when you take a unit cell of HCP, okay, this is how it looks. All right. So this is the AB type of packing. You can see the first layer, third layer being identical to each other. All right. Now this is the unit cell of HCP. You can see here the unit cell from HCP represents a body-centered cubic unit cell. Okay. Now coming to the three-dimensional cubic close packing, or the CCP type, where I told you that the third layer will cover the octahedral voids. So you can see here, this is the first layer represented as the A layer, the second type, layer of AB two-dimensional arrangement, that is called as the B layer now, and the third layer again having the AB type of two-dimensional arrangement, now called as a C layer. So when the B layer fits on the A layer, it will give rise to octahedral as well as tetrahedral voids. But if I position the third layer in such a manner that it will cover only the octahedral voids, like in this case, then you can see that the third layer's alignment is different from that of the first, and hence it can be called as layer C. So this will give rise to a cubic close packing of the ABC type. Now again over here, the coordination number of the central atom here in this particular plane, that is in layer B, will be 6. There are 3 more atoms coming from the third layer on the top, that is the C layer, and 3 more atoms from the bottom layer, that is the A layer, will also be in contact with the central sphere. That means again the coordination number here is 12. Okay, and you can see here how it gives rise to the octahedral geometry, because the octahedral voids are getting filled up. Okay, and this is the cubic close packing. All right, now the unit cell of this particular three-dimensional packing, so this is how the coordination number can be calculated again in the cubic close packing, that is 12. Okay, 6 in the same layer, 3 above it, and similarly you will have 3 below it. Okay, so the coordination number becomes 12. Now this is the unit cell of the cubic close packing. You can see here the unit cell is of the FCC type. And that means in FCC, you know, the number of atoms is maximum. In the unit cell, you can have 4 atoms in FCC. And therefore, the packing is supposed to be the most efficient in terms of the space occupied in the cubic close packing of the ABC type. Okay. So that's all for today. I hope you've understood how the three-dimensional packings take place. So if you like my videos, please subscribe to it and keep watching and referring it to all your friends. Thank you and see you soon in my next video.